Ideal flow, and in this lesson we are going to look about the coordinate system that we will use to solve problem in ideal flow. So there are two coordinate systems being used in this chapter. One is Cartesian coordinate and the second one is the polar coordinate. The idea of these two coordinates is already taught in previous lesson. But however, to make sure that you really understand about these two coordinates, I will explain again in this chapter. So the first system is the Cartesian coordinate system. A Cartesian coordinate system is a coordinate system that specifies each point uniquely in a plane by a pair of numerical coordinates, which are the signed distance to the point from two fixed perpendicular directed lines measured in the same unit of length. Each reference line is called a coordinate axis or just axis of the system, and the point where they meet is its origin and ordered pair 0, 0. The coordinate can also be defined as the position of the perpendicular projection of the point onto the two axes, expressed as signed distance from the origin. So this is the example of the Cartesian coordinate. I think all of you is familiar with these coordinates. We have the x-axis here and y-axis here, and normally x-axis is horizontal and y-axis is vertical. So for example, we have one point here, so we note this point is 2, 3 because it is 2 units in x direction and 3 units on the y direction. So we must write it from as x and y. So if we have one point here, so we write this point as -3, 1 because it located at -3 on the x-axis and positive 1 at y-axis. So I hope you could write this very well because I think you're already familiar with the Cartesian coordinate. So for example, we have a molecule here with coordinate x1 and y1. So after a certain time, this molecule move from this location to this location with the coordinate of x2 and y2. So the velocity might be equal to small q here. However, if we look from the idea of component velocity, we could say that this molecule will have x-axis component molecule written as small u here and y-axis component velocity which is written as small v here. So we could say that this molecule has component of u velocity and v velocity. So we could please remember that u is the velocity on x direction and v is the component velocity on y direction. The resultant velocity can be calculated by using this equation, square root of u squared plus v squared. So this is the second system that being used in this lesson. It's called polar coordinate system. In mathematics, the polar coordinate system is a two-dimensional coordinate system in which each point on a plane is determined by a distance from a reference point and an angle from a reference direction. The reference point, analogous to the origin of a Cartesian coordinate system, is called the pole, and the ray from the pole is the reference direction is the polar axis. The distance from the pole is called the radial coordinates or radius, and the angle is called the angular coordinate. Sometimes it's called polar angle or azimuth. So this is the example of polar coordinates. We just imagine that we have one molecule here that move in circular direction like this. So to locate the location of this molecule, we are not using the location of x and y, but we are locate or we give coordinates of this molecule by expressing the location in terms of r, means the radius of this molecule from the origin of this circular path, and the angle, the theta that made by this molecule. So we write as r and theta. So for this location, the radius is r and the angle is theta. So the coordinate for this one can be written as r theta. And then this molecule also have the component velocity. So we write as ur here is the component velocity on radial direction, the axis that parallel to the radius here. And another component velocity is u theta, mean the tangential velocity of this molecule regarding to the angle of theta here. And then the resultant velocity can be expressed as this arrow, and it can be calculated by using this equation. So the resultant velocity is square root of ur square plus u theta square.